Hi, everybody. My name is Bobby Holly. I'm B. Holly on IRC. Apparently, I'm old guard, if you count my internship. I started hacking on things in 2008. Yeah, Jerv. And for the past 3.5 years, I've been working mostly on what people know of as like XP Connect or scary security stuff. And it's been interesting, and it's been quite a lot of fun. This talk is a follow-up to one that I gave in Brussels last year. As a brief measure, how many people who are paying attention to the talk saw the talk at Brussels? Okay, how many people didn't see it? Okay, and I'm assuming that all of the people who didn't see it would appreciate some level of review of the material you didn't see, right? Okay, great. So I've planned some of that in. So yeah, I'm going to go through that stuff like a little bit faster maybe than I did before, not go quite into as much depth, but we have this awesome 2-hour slot. So feel free to raise questions at any time, and I'm happy to talk in more detail. When I gave this talk last year at Brussels, for me it was really, well, not this talk, the previous talk. It was a celebration of how far we'd come, right? Because we were really kind of in the dark days in security-wise for a number of years. And by the time last year rolled around, we'd really started to settle on a very solid, very secure architecture. And it was one of those things where, we knew that there was more to do, but there was kind of this feeling that, all right, like finally, we're kind of almost there, we're on the right track. And then really just like a week or two after I gave the talk at Brussels, some security bugs started rolling in, specifically around the stuff that we knew we still had to do that lent it a lot more urgency. And this is specifically around the area of JavaScript implemented web APIs. So we had kind of gotten a little bit ahead of ourselves in all of the rush to ship B2G and used a bunch of technologies that we didn't really think through and a bunch of stuff that wasn't quite ready. And it became clear that, we were actually in a pretty bad place. So I kicked off this project called Slaughterhouse on October 24th of last year. The name Slaughterhouse came sort of, it was sort of a two-pronged joke, right? The first part was that the most insecure of all the technologies we were using were these things called Chrome object wrappers, or cows. These are the exposed props things. Those were cows. And the idea was that we wanted to kill all of the cows, right? So that's where Slaughterhouse came from. But Slaughterhouse was also kind of a recognition in my mind of kind of how dead we would be if we started getting slammed on this stuff. Because it was scary not insofar as we had one or two particular security bugs, but that the types of security bugs were in code that was doing something that didn't really look all that weird or all that abnormal. Which meant that we probably had quite a lot of these cases, right? It was just people doing normal stuff in JavaScript when they were implementing those web APIs. And if that can't be secure, we were not really in good shape. So over the past year, there was a lot of churn. Slaughterhouse was an awesome project. I did a lot of the work, but lots and lots of other people helped out. People on different teams writing patches, Gabber and Boris reviewing hundreds of my own patches. And most importantly, I would like to thank all of the people whose code and tests, or lack of tests, that I broke. There was lots of B2G stuff that didn't have particularly good CI coverage, and lots of stuff that broke, and people were generally really good sports about fixing it up. And I really appreciate that, because it wouldn't have been possible to get done otherwise. So about a week or so before October 24th of this year, I landed the last patches to really finish off all of the stuff we needed to do for Slaughterhouse. And so in my mind, this is kind of the mission accomplished moment. But it's not only really mission accomplished for Slaughterhouse, but it's kind of mission accomplished for the grander re-architecting of all of our script security architecture and all of that crazy, weird XP Connect-y stuff. And so I know that every time I've told people about how this stuff works, or before me probably talking to Blake, it was always this thing of like, forget all the stuff I told you last year. That was totally wrong. Here's how you do it now. And next year we're going to change it again. And I'm hoping that that's not going to happen anymore. I've sort of joked that this might be my last talk that I ever give about wrappers ever, which may not be true because I really like doing it. But hopefully it's the last one at least that you need to come to. Because this stuff is basically stable, which means that it's a really good opportunity for everybody to finally fully page into your head exactly how this stuff works. I'm going to have some flowcharts, some little diagrams of how you can simulate in your head, depending on what situation you're in, what the security properties are, what wrappers you're going to get, and why all that stuff makes sense. And then I'm hoping that everybody can then go on and answer their own security questions and answer security questions for all of your friends, and then we're all happy. So I'm leaving some time, tons of time, for question and answers at the end. But you should also feel totally free if something doesn't make sense or if you want more explanation. Just raise your hand. I'm happy to go into more detail about anything. This stuff is all obvious to me because I've been steeped in it for 3.5 years, but it's not really obvious to anybody else. So, if it's too fast or if I miss something, just raise your hand. So, the obvious point, the truism that I've sort of learned while working on this stuff is that securing untrusted JavaScript is kind of a hard problem. And this was even really mentioned, I think, in one of the keynotes yesterday or the day before. It's like, what other technology platform just goes and loads a bunch of untrusted code from the internet and then executes it on your local computer? But I think it's not obvious to everybody, right? Like, when people ask me what I do for a job, I say, well, I work on security. And then people say, well, do you go and somebody call you at 2 in the morning and say there's a hack going on? Well, not really. I try to design things such that the hacks can't happen. And for most people, that's, they kind of nod and say, all right. But specifically, technical people like programmers who don't work in the sphere of web browsers are usually a little miffed by that. Because they're like, what do you mean you design it that way? Right? Like, the web has been around for 20 years, right? Presumably the web was designed securely or not securely. And if it wasn't designed securely, then what the hell are we all doing using it? Well, maybe we should be using something else. But it really speaks to the fact that the web wasn't really designed, and it certainly was not designed with security in mind. And I think at the very beginning, security, real security kind of seemed superfluous because the whole thing was such a toy anyway that why would you really need it to be secure? And it was only as time went on, as people started doing interesting new things that nobody could have envisioned before, like online banking and communication and images and government stuff, that it started to be juicy targets to exploit, stuff that was actually worth going and finding clever exploits for. And the browser vendors really had to struggle to keep up. And it got a lot better. But from the beginning, there were just a lot of APIs that were neither designed nor implemented carefully at all. And the stuff that wasn't implemented carefully, stuff that has security holes, fuzz bugs, that stuff we could pretty easily make progress on. We could find these things, we could improve the code, we could rip out stuff that we weren't using. But the JS observables, the APIs, the structure that we were essentially bound to supporting, the design problems in there hurt us a whole lot more. And it basically, hurt all web browser implementers and everybody's security. Because improving that stuff faces enormous compatibility and interoperability constraints, right? You can't just go, okay, Jesus, that was a bad idea. Let's get rid of this whole DOM thing. Let's stop allowing process properties cross-origin. You can't do that because then websites break. So it's been slow going. And I think the best example of, that I'm most familiar with of how this works or of how this has gone is with what everybody knows as the same origin policy, right? That code from one domain is allowed to interact with other code from the same domain, but not code from other domains. And the specifics of script access across origins was not particularly well designed. Apparently, I just talked to DVedits half an hour before the talk, and he says that I should actually give Brendan more credit than I did, and that he was thinking about it, right? But that there wasn't really, there wasn't a plan, and it was kind of just, thinking about these, looking at this cross-origin access and deciding on a case-by-case basis. Yeah, I think that one's okay. Yeah, I think that one's not okay. And this process basically happened differently with all of the different implementers, right? Because Internet Explorer had a very different set of cross-origin properties that were accessible than Netscape and Mozilla did. WebKit had a different set still. And so this stuff was not at all well-defined or consistent, right? I'm pretty young, and I remember feeling really dumb back in college because I could not find the spec for the cross-origin properties on the internet anywhere. And it turned out, in retrospect, that the spec didn't exist. It was actually an about config pref that we shipped in Firefox, so you could change it. Every user could set their own cross-origin policy. And it was literally less than a year ago, last December, that some of us, like me and Hixie and Abarth, finally sat down to start writing the specification for how this stuff works, right? So really, designed is not the word we want to use here. But the fact that there were such diverging implementations really saved us in the end, right? Because the stuff was so different between browsers that very few web pages were actually depending on it, because you would write it in one browser and it would work, and you'd write it in another browser and it wouldn't. So we managed to, piece by piece, shave off all of these different things that were not available in all of the different browsers until we got to the point where you could basically do very little, next to nothing, right? Which was great. So if you want to ask now what the story on the web is for how to communicate with cross-origin code, the answer is basically you don't. And if you really want to, you use message passing, right? Post-message. We think of post-message as being this thing that is core to the web platform and that has been there forever. If you go find the bug, it was like 2007 where we implemented it. And it wasn't because like any word came down that we needed to implement it. It was because Waldo was like writing a mochi test, and he was sick of what you had to do before. Like the way you did this before was the location.href or .hash was cross-origin writable. So you would dump information into the hash of the cross-origin page, and that thing would be polling on a post-message loop and pull the stuff out. And then it would come up with a response and dump that back into your location.hash, and you would have a post-message loop, or a set timeout loop pulling this thing out, right? That was how you did it in 2007. So
what's wrong with that?
Johnny invented the DOM, by the way. But now we have post-message. And post-message basically looks like this. Right? This is how web browsers want you to do cross-origin communication today. There is a very strong boundary. You cannot directly interact with code. You can create a message, you can pass it to the police officer here, and it gets, inspected for cigarettes, and then you put it on the other side. It's actually cloned, right? The same data, the same actual objects are not accessible. And that is sort of the state of the art on the web today. And it's cool because our architecture lets us enforce this kind of solid barrier better than any other architecture out there, better than any of the other engines. I guarantee you, they have security bugs that come up that are not security bugs for us. But the web itself basically ends there, because that's all there is. On the web, there's only stuff that is same origin and stuff that is cross-origin. If you have the same domain, you can communicate. If you don't have the same domain, then you have to use this. There's no notion of anything else. But Gecko is more complicated. So what we have in Gecko is this notion of privileged, trusted JavaScript. And it's a proprietary technology. It doesn't exist in other platforms. And you will hear implementers of other platforms scream very loudly at any suggestion that this ever leak into the web platform, so it probably won't. But we're stuck with it. And it seems, maybe like a dumb idea, but it came from a very radical idea of self-hosting the browser, right? Like in the early days, everything was written in C++. All of your UI, all of your API implementations. You had to maintain different front ends on different platforms. And then somebody came along, I think it was like the late 90s, and had this idea that we would start writing our browser itself in JavaScript, which was a crazy idea for the time, right? JavaScript was a toy language. Why would you do that? I think that if we were to do something like that again today, we would probably do something more like B2G and Gaia, where we would say, all right, let's do something like the web, and let's fill the gap of APIs wherever there's something we can do to let us do it. But that was 15 years ago, and the web was totally not there. So if we wanted any chance of having a real viable application, we had to create JavaScript that could do anything. JavaScript that could read and write files, that could execute code, that could do everything that C++ could do. But when you come along and try to have a security model for this sort of JavaScript, it's weird because it's all powerful, right? So you can't just sandbox it. You can't tell it no ever. You can't say you can't do that because the JavaScript is all powerful. So, the obvious and our original solution was just like, well, sweet, like, job done. We don't have to have a security architecture because the code can do whatever it wants. But then we get security bugs, right? We get these bugs where front-end code in the Firefox engine, in Firefox, or web API code goes and does something that causes a security bug because of its powerful privileges being misused, right? And when I see that, or the old version of me sees that, the obvious response as a platform developer is like, well, God, like, don't do that. Like, don't make security bugs. Don't do stupid stuff, right? But that's not really good enough. So I don't know how many people here know about American politics. There was a big thing over the last month or two about Obama's internal foreign policy directive of don't do stupid stuff, right? And there's a big debate in the newspapers about whether this was like good advice, like yeah, just use your head, or whether it was stupid and vapid and caused us to get into lots of foreign policy kerfuffles. And in my opinion, the answer to whether or not don't do stupid stuff is good advice depends on whether the people you're talking to can A, reliably identify what stupid stuff is, and B, once they've identified it, whether they can reliably avoid it, right? And in Gecko, we really had neither of these things. And that was the source of a lot of our security bugs. Because the target audience of this whole API platform of privileged JavaScript, these are JS hackers, right? These aren't people who are steeped in the intimate details of caps and saved frame chains and all the other crazy JavaScript stuff. So, and there was sort of this also unfortunate meme perpetuated by upper management back in the day of like Shaver and Brendan of like, let's just write it in JavaScript and then we don't have to worry about security, right? And this was kind of unfortunate. But even aside from this lack of focus on security on the JavaScript side, there was also the fact that JavaScript as a language itself, people talk about C++ being an unsafe language, but what we do with JavaScript is super unsafe. Right? If you go to people in academia who research security and you say, yeah, well, we have this dynamic, loosely typed programming language where we have really privileged stuff and unprivileged stuff, and it all talks to each other, and they share object references, and they've got dynamic functions, and there's eval. Like, they're going to think that you're absolutely insane for shipping a product with that. But we do. So in that world, even the most paranoid, carefully constructed code, if you're writing a lot of it, has about a snowball's chance in hell of being secure. So what we needed to do was to fix it in the platform. And that's what this is about, right? I'm sure a lot of people who've worked on XP Connect, myself and Blake and Boris and Johnny, and many times would have loved to say, this privileged JavaScript thing, it was a bad idea. Let's just back it out, right? I mean, Stuart used to joke about backing out Zool, but this is kind of the same thing. But even if we could, and even if we didn't have all of this legacy code that used it, we gain a ton by being able to implement stuff like this in JavaScript, right? We gain a ton from being able to hire the best application developers to work on the Firefox team and not have to quiz them about singly linked list manipulation in C, right? We gain a ton from being able to rapidly implement web APIs by people who write specifications who don't have to worry about, garbage collection and cycle collection. Maybe they do a little bit. But this is a really powerful technology, and it's one of the things that lets us, it's one of our David and Goliath tools that we can leverage. And the idea is to make it such that writing secure JavaScript code in these contexts is not rocket science. So I'm not saying that you don't need to think about security if you're doing that. You still absolutely need to think about it. But the point is, if you're thinking about security, if you're being reasonably careful, secure code should be achievable, right? It shouldn't be only the person who maintains XP Connect who can write secure code. It should be everybody who's thinking about what they're doing. So the basic idea here is that at the end of this talk, I'm going to say, don't do stupid stuff, and that should be enough. No more security bugs. So I'm going to review sort of some of the basic architecture of how all this stuff works. This first part is going to be pretty heavy review from the other talk that I gave last year. But it sounds like a lot of people want it. The people who know it all already, feel free to dive into your laptops, whatever. So the first idea is this separation, in a way, between the JavaScript engine and the DOM. So if you're programming on the front end or just programming as a web developer, all you really interact with is JavaScript, right? You have your JavaScript objects, you have your arrays, you have your typed arrays, you have your document, you have your window. And they all just feel like objects. But under the hood, we actually have two separate sets of objects, two separate heaps, different regions of memory in which these objects are stored. We have the JavaScript heap, which is what you interact with when you're running script. And then we have the C++ heap, or the DOM, right? The boundaries between these things are becoming a little more fuzzy as time goes on, but this model still very much applies. And the reason we have this stuff in C++, well, part of it's historical, right? Back when everything was in C++. But it also needs to interact very closely with things like layout, which is written in C++, and stuff like graphics. We've tried self-hosting all of the DOM in JavaScript. It didn't really get very far. So the basic idea here is that this is the canonical representation of your document, the stuff in the C++ heap. That's the stuff that gets generated out of the HTML page that you load. But then over there, you've got the JavaScript heap, right? And I think everybody's very accustomed to interacting with these things over there. So how does that work? Well, we have this thing called reflection, right? Reflection is the idea that when you want to interact with something in the C++ heap, we create a JavaScript object that reflects that represents that object, that acts as its agent. So we have these in a couple of different ways. The classic way we would do this was with XPC wrap natives, which is via XP Connect, we have this ability that anything that implements an XPCOM interface can be accessed in JavaScript using the tools of that interface. It turned out that that was really slow, and so recently, over the past couple years, we've written what we call the new DOM bindings, or just DOM objects. So these aren't generic, they're code generated at build time, and they're much, much faster and more spec compliant. But either way, the basic idea is that we have the C++ object, and then we create a JavaScript object that represents it. And what we do in order to interact with those objects is that for each of the items of the C++ methods that exist on these C++ objects, we create JavaScript methods, JavaScript getters, JavaScript setters that mimic those operations, that forward down. So when you invoke the first child getter on the body element that is reflected into JavaScript, that invokes a function that is a specialized function that then tunnels down across this boundary, converts all of the arguments, if there are any, between the JavaScript language and C++, and then invokes the actual underlying C++ method. So if you ever look in a debugger and you do a backtrace and you see stuff going from JS interpret and then suddenly you're in C++, that's what's going on. So these things obviously get forwarded, but I think a lot of people are accustomed to the fact that you can actually stick any property on an object, and it works, right? You can do document.foopi equals 2. And that foopi property obviously does not trickle down into C++, because the C++ representation of the document is a fixed region of memory, right? It doesn't have space to put whatever extra properties you want on it. So this is what we would call an expando property, or just a regular JavaScript property that does not reflect any DOM behavior. You can stick these things on, and you can manipulate the state of the reflector to your heart's content, right? Let's say you can delete onClick, or you can delete getElementById as a property, or you can change it to a different function entirely. You can make the JavaScript world of your page whatever you want. That may be a historical design mistake, maybe it's not, but that's the way it is. But none of that stuff actually affects the underlying C++ representation, which is the canonical representation of your state. So this is what the JS heap used to look like, right? In the previous slide, we saw just one global. But in actuality, even if you start up Firefox today, without opening any tabs, you have about 200 globals. And then when you open tabs, you get a lot more. So a global object is your window object or your this object. Well, anyway, it's different things in different contexts. But a global object is every piece of JavaScript, every JavaScript object is associated with a global. So this was kind of a problem, both from the perspective of garbage collection, as we started to have more and more of these things, and from the perspective of security, because everything was all tangled up, right? So when you have 200 tabs open, and only one of these tabs is generating garbage, it's a real shame if we have to piece through all of that mess to get to the one bit of garbage that we need to collect. And at the same time, it's also really bad for security to have all this stuff tangled up, because even just the idea of your bank stuff and your gambling website stuff just kind of being all scattered together is kind of scary. So the really key observation here is that most of the interesting boundaries, specifically from a security perspective, happen at the boundaries between globals, right? Most of the things that belong to the same global generally have the same security properties. There's no difference. There's no need for any security checks between them. But when you cross globals, that's when stuff happens. And so that's why we did compartments, right? Compartments eventually became compartment per global. And the idea is that we put all of the objects belonging to a single global into the same region of memory, right? This isn't quite true. I'll tell that in a sec. But the way you can think about it is that we separate all of these objects into separate heaps. When these things are in separate heaps, there's no question about what global something belongs to, because you literally just examine where it is in memory. And what that also means is that if we have these separate heaps and we can compartmentalize the boundaries between the two of them, it makes garbage collection much, much faster, because we can just garbage collect one of the tabs rather than all of the tabs. So in terms of garbage collection, we actually cheated a little bit, and Blake corrected me about this last year. We have zones now, right? So you basically don't need to worry about zones. Zones are a separation. It basically turned out that from a security perspective, we really wanted the boundaries to be around globals. But from a garbage collection perspective, we really wanted it to be around tabs, right? Because tabs, even if Twitter has a bunch of iframes, that's kind of the unit of garbage. And so we sort of separated them out, right? So the actual physical reasons of memory are zones, and stuff from zones within the same compartment, stuff from the same compartment, or from different compartments within the same zone can exist near each other in memory. But from the perspective of anybody who's interacting with it, you don't need to worry about that, and our variants are still very solid. Like, this happened for like a year before I even realized that was happening. So the key to hygiene, specifically security hygiene with all of this compartment stuff, is this idea of entering a compartment, right? Gecko, can only interact with objects and functions and code and scripts from one compartment at a time. And so we have this notion of entering a compartment, where Gecko says, all right, I am now going to interact with things in that compartment. And it's a very exclusive relationship, right? So you can sort of imagine if these compartments are like little houses, Gecko walks into one of the house and says, I'm going to now interact with all of the objects in here. And if I want to go and interact with things in the other compartment, I have to leave this house, walk next door, and enter that door. So this is really important because it means that our boundaries stay secure. We don't have to worry about things leaking between little references and pieces of information leaking between our compartments, because we know that the engine itself is only touching objects from one of them at a given time. This is very, very strongly enforced. Now, I know you're probably thinking that, well, yeah, but I interact with things from different globals in JavaScript all the time, right? You just create an iframe, and then you go into content window, document, etc., and suddenly you're accessing things in another document. But you're not actually accessing those objects in the other document. You're accessing what we call a cross-compartment wrapper, right? This is a proxy object. It's not actually the object that that you think you're interacting with, but it is an object that lives in your compartment that represents things on the other side of the boundary. These are special delegates. These are objects that are specifically allowed to cross between compartments, and effectively they are the agents or the proxies of those objects you're interacting with that all live inside your own compartment. Now that's really cool, because it means that we can create what's called a security membrane. Because whenever one of those proxy objects, you say, hey, I want to get this property off of you, and then the proxy object says, wait, okay, sure, and then runs to the other house, figures out what that property is, and brings it back. And if that property that it brings back is also something in another compartment, then it doesn't bring the property itself back. It brings back another proxy. And as long as the original objects, it's like Plato's allegory of the cave, as long as the original objects are never actually seen by the code in the compartment, it cannot tell the difference. And this is really important because we expose this stuff to the web, right? Compartments are running all the time. You always have cross-compartment wrappers between any two globals. But the spec has absolutely no notion of this, right? So the only way we can get away with shipping it is the fact that these wrappers are absolutely 100% transparent. There is no way to notice that you are interacting over a wrapper if that wrapper is one of what we call a transparent cross-compartment wrapper. So you can sort of think of it as like a wall of latex between these two heaps, right? You can sort of reach through, you can grab something, and you can hold on to it. But you still have this membrane between you and the stuff on the other side. And we have very, very, very heavy dynamic enforcement of this with our compartment mismatch assertions. We have these things even turned on nightly so that if extensions do anything nasty, we find out about it. Because even if there's one leak across the membrane, the security membrane is not doing its job anymore, and effectively we have an SG crit. So I remember we used to have quite a lot of compartment mismatches. I don't really see a lot of them anymore. Maybe people just aren't telling me, but I think that means that we've mostly sorted out the mismatches that we have, and with our WebIDL machinery, the sources of mismatches that tend to come up. So if you see a compartment mismatch, take it seriously. Any questions in the meantime, by the way?
Can you give us a fun example?
A fun example of?
Of a mismatch.
I mean, mismatches, like in...
Can you repeat the question?
Oh, sorry. Marcos wanted a fun example of a compartment mismatch that came up.
Who can introduce the mismatch? What type of code?
Only C++ can introduce a mismatch. Sorry. Thank you. The question was, who can introduce a mismatch, a compartment mismatch? Only C++ can. So if you're just working in JavaScript, you don't have to worry about it. If you're in C++, if you change compartments, you have to invoke JS wrap value or JS wrap object. But really, unless you're working on the DOM bindings code, like unless you're me or Boris or Kyle or one of these people, for the most part, you should not be interacting with compartments or with JS objects directly, right? You should be using the DOM bindings helpers and all of this stuff that does that magic under the hood. But yeah, if you ever do enter a compartment and you use an object that you had before, you have to make sure that you call JS wrap value or JS wrap object on it. Examples of a fun compartment mismatch, I'm not really sure. I mean, they exist in NS, HTML document, : something, and the fun is that you crash. And if you don't crash, then we have a security bug. So the cool thing about compartments is that they give us very clearly the building blocks we need to make security decisions, right? A lot of security decisions inside the browser boil down to two things. First, what is the origin of an object? Where does it come from? What domain does it belong to? What is its principal? That question is very easy to answer because the origin is attached to a global, right? So all we need to do is to figure out which compartment the object lives in, which is simple. You simply look at the object and, from the perspective of the JS engine, the answer is obvious and unequivocal. And then you examine that global and determine what its origin is. So that question, which used to vex us terribly, is now simply solved. The other question is, who is the subject principal? Who is the caller? What is the calling code? Who is responsible for the code that is being executed right now? And this is particularly cool, because in JavaScript, functions are objects, right? So functions and all the code that executes actually lives in a compartment along with every other object. And because manipulating objects requires us to enter the compartment, we know that whatever code we're executing, we must have entered its compartment. Otherwise, we would have had a compartment mismatch. So that gives us an incredibly powerful invariant. We can simply say, what compartment is Gecko in right now, and know that that is the origin of the caller. Even in situations where the JavaScript engine calls down into 20 call frames of C++. We simply look at the JavaScript state of Gecko, examine what compartment it's in, and that will tell us the origin or the principal of the innermost, most recently executed piece of JavaScript code. So, yeah, that's great. But the wrappers are really, I think, where the magic is. And these things are very, very important for Mozilla and a lot of things that have helped us and are helping us survive. The cool thing about wrappers is that they don't exist in the common case, right? Because the common case of JavaScript code is stuff interacting with other things in the same global. So in that case, everything is same global, there's no cross-compartment wrappers, and everything operates 100% at light speed. The JIT can do its stuff, there's no security checks at all. In the uncommon case, which is when stuff is crossing compartment boundaries, that is when we create a wrapper. And it also so happens that this uncommon case is the only case where we have interesting security properties that we need to worry about. So it's really cool from a performance perspective because we don't have to hamstring all the stuff that runs on Dremio. Even then, though, in situations where we have code interacting same origin, right? If you just have two same origin iframes, we still don't have to do a lot of security checks. We simply do the check once when we compute the wrapper, when we say, OK, we're accessing things from this compartment in this compartment. We need to create a proxy for it. We need to create a wrapper. And then we notice, yeah, these things are same origin. So we just create the simplest, fastest, transparent cross-compartment wrapper, what we call the vanilla cross-compartment wrapper. And after that, no security checks need to be performed. We just have a proxy that forwards this stuff across the boundary. But the really cool thing about wrappers is that they are flexible. We can do anything or almost anything we want at this boundary. We can create arbitrary labyrinths of fun. And this has been really important for us because it saved us basically on E10S, which is, I'm going to explain a little bit at the end. But these kinds of wrappers and proxies have, they were the core of Kapow's and of our add-ons compatibility story. And more importantly for me, they also saved us on Slaughterhouse, because we had to do an incredible amount of finely grained security work in order to balance compatibility with all the existing code and security. And the only way we were able to do that was the fact that we could program the hell out of that security membrane and put in exactly what we wanted. So these security wrappers, they have what we call bidirectional protections, right? And I think when most people think about security wrappers and accessing things, across trust boundaries, they normally only think of the first case, which is that, well, you have some untrusted code reaching across the boundary to stuff that it doesn't necessarily have the rights to see, and you don't want it to see everything, right? That's what we would call a filtering wrapper, right? It's applying a filtering policy, which is anything from show me most things to only show me a couple things to show me none of the things. And that is what we use to protect code from code that it does not trust, that is accessing it. But we also need protections in the other direction. And this is what we call X-ray wrappers. The basic idea is that if you have system code, Chrome code, or just other kinds of privileged code that is accessing content, untrusted code, stuff that it does not trust, it's very easy for that code to get confused by very, very clever content that redesigns everything in the JavaScript world to be a little bit funny, to be, kind of one of these garden paths. So, for example, let's say you have front-end code that wants to go get the first, that wants to do something to the document of the tab that it's dealing with. But that content could have deleted the document property off the window and instead replaced that with a getter that returned an entirely different document somewhere else. And if the Chrome code just blindly goes along and says window.document.body.firstchild, they are suddenly going to be accessing something that is not what they expected. And they can do all sorts of things, right? They can return different documents. They can spin the event loop. They can return proxies that generate arbitrary worlds of confusion and misdirection for this privileged Chrome code. And this privileged Chrome code is basically walking around with a machine gun or an atomic bomb or however you want to look at it. It has the ability instantly to do something that entirely compromises your security, which for some reason in the security world is launching calculator.exe. That's sort of the proof of concept that we use rather than like deleting your C directory. But that Chrome code has the ability to do that at any moment. And so it's very dangerous to have it ever be in a situation of confusion where what it thinks is doing is not what it's actually doing. So the solution to this is what we call X-ray wrappers. If you think back to the diagram a couple slides ago where we have the JavaScript heap and we have the C++ heap, all of the funny stuff happened in the JavaScript heap, right? That's where you delete properties, rename properties, move properties around, put different funny getters and setters on everything. The C++ heap is kind of static, right? It only changes in predictable ways because it's old and stodgy in C++. So what we do with X-ray wrappers is that when you're accessing code that you do not trust, like basically when Chrome code is accessing untrusted content code, it gets what we call an X-ray wrapper, which gives it a clean view of what's going on, right? That filters out all of the junk, that doesn't look at the reflector that content may have played with, and looks directly at the underlying object. In a way, it kind of gets its own reflector. It's a little more complicated in the proxy land, but that's the basic idea. And that works very well because we have the C++ code, and the C++ objects are very well defined. We know exactly how they work. But this started to be a problem, and this is one of the core pieces of Slaughterhouse. Because I remember, originally asking Blake when I started working on XP Connect, what happens if you want to X-ray to a JavaScript object? And he sort of looks at me and he says, well, what would that mean, right? You can't X-ray to JavaScript. There's just more and more JavaScript. There's nothing else. And that kind of convinced me at the time. But then we started having security bugs. And a big part of these security bugs was the fact that as time has gone on, the DOM and JavaScript have become more and more intimately intertwined, right? We're no longer holding this idea that maybe we're going to run Python on the web anymore. So all of the specs start to interact more concretely with JavaScript and to return JavaScript objects. And then there are objects that aren't clear whether they're JavaScript objects or DOM objects, or the distinction feels very arbitrary, right? Like the fact that a date is a JavaScript object and not a C++ object is kind of arbitrary. The fact that a promise is supposed to be a JavaScript object but is implemented as a C++ object in Gecko is also very arbitrary. And we've got this with lots of things. We've got typed arrays, functions, errors. All of these things are things that we're starting to need to interact with from privileged code, but that we didn't really have a security story for. So this was this project that we launched called X-Ray2JS. It was part of Slaughterhouse. And the basic idea was to, fight tooth and nail, just move piece by piece and implement reasonable security protections for all of these types of objects that you might want to interact with, right? So the easiest ones to do were the ones that had very sane and understandable behavior of how they were supposed to behave, right? These were ECMAScript objects like date, typed array, function, error, things that have a prototype, things that have understandable properties of how they're supposed to behave, and that have underlying C++ state. So for these, we literally went through and one by one custom wrote X-ray wrappers for all of these different types of objects. There was some shared code, but there was a lot of manual stuff to be done. So effectively, you get your own version of date.prototype when you're accessing an X-ray date object. And when you operate on that date object, the methods you use are not the ones inherited from the contents date.prototype, but from your own date.prototype. So that ended up working very well. But then there was the trickier issue of what to do about objects and arrays, right? Because, for those who, haven't yet found out about the horrible news, arrays in JavaScript are actually just objects, right? They're objects with a length property that does a couple things, but there's nothing really different from them from objects. And these things are weird, right? Because objects don't have any of this behavior like date. They don't have any underlying C++ state. They don't have sane methods of interaction via the prototype. You're literally just putting some curly braces and saying, this is one property, this is what it has. And so it would be nice to simply ban access to objects from privileged code over these JS X-rays, but that turned the entire tree orange and broke a whole lot of code, especially these funny little B2G APIs. So what we did was we just went through all of the possible types of security issues that we might have with these things and filtered the objects very carefully. Because the key insight is that most of the stuff people want to do with objects over X-rays are just treating the thing like a simple dictionary, right? You've got the foo property, which has a string, and something else which has an integer, and something else which has a float, and something else which maybe has another object containing the same things. There's not a lot of funny getters and setters. There's not a lot of methods. There's not a lot of this tricky business. So what we do is we disallow, first, we disallow accessor properties, no getters and setters when accessing over object X-rays. We disallow non-subsumed values, so properties that the object being accessed doesn't have access rights to itself, right? So if the object has some pointer to a cross-origin window or location, you're not allowed to see that over X-rays. We disallow access to non-X-rayable objects. We disallow access to shadowing properties, right? So if you decide to override the .bind method on a function, or on an object, let's say you want to override toSource, that's not going to work. And we also, perhaps most controversially, disallow callables. Because most of the problems that happen when Chrome code is interacting with untrusted code happens when Chrome grabs a function and accidentally or on purpose and at some point executes it. So we just say that that's probably more likely to be a security problem than not, and we turn it off. Then finally, there's all this long tail of other ECMAScript objects that would have been quite a lot of engineering work to implement, and we didn't have time to do. But rather than doing what we did before, which is just saying, OK, we don't have X-ray protections on those things, we flipped the switch so that those things are opaque by default, right? And this is huge. This is one of the key pieces that makes our code so much more secure than it was 1 year ago. Because now you don't have to worry, like, oh, I have this object. Like, does it have an X-ray wrapper? Maybe it doesn't. Maybe I think it has an X-ray wrapper, but it's actually some other type of object that we don't have the ability to X-ray. If we can't use it safely, it's opaque by default, which means that you don't have to worry about it. The flip side, though, is that sometimes you do actually want to interact with these objects. And we have a safety valve, right? This is called waving X-rays. You probably know of this more by the .wrap.js property, but you can also do it equivalently with components.utils.waveXrays and components.utils.unwaveXrays. The latter is a little better because if you happen to use it on something that isn't itself an X-ray wrapper and therefore does not have the .wrap.js property, your code isn't going to throw property not found error. The basic idea of waving X-rays is that it is an explicit decision on the part of the person writing the code to waive the normal protections that we give you. Now, that means that you have to be very, very careful, but there are situations in which you need to do it and can do it safely. X-ray waving is transitive, which means that if you wave X-ray on a property and then you access other things, all of the things that come back are X-ray waivers as well. And X-ray waivers are also a separate identity, right? So if you wave X-ray on an object, like foo.wrap.js object does not equal to foo, because they have very different behaviors, and we wanted to represent them as different objects. So I know there are situations where people need to use these, and that's OK. But the point about it is that it's a very explicit decision on the part of the programmer to do something that is potentially unsafe. And this idea you see in a lot of other situations, for example, in Rust, where we have unsafe blocks, right? Because we wanted to create a systems programming language that allows us to compete with C++, but at the same time is safer than C++. And there are some things that you can only do in really crazy unsafe code. But 99% of the time, you don't need those, and those are more likely to be a security footgun than they are to be something useful. And so in Rust, you have to put your unsafe code in an explicit unsafe block, and that's when you can do that. In JavaScript, you have to explicitly wave X-rays. So if you're reviewing code, be very careful about that part and recognize that all of those properties and all of the things that you pull off of it until you unwave X-rays are not going to have the X-ray protections that make you safe by default. So don't do stupid stuff. So this was another big part of Slaughterhouse, the dead cows. Cows were a real major problem. And I know, I understand that it was kind of confusing from the part of JS developers, because for a while we were saying, like, everybody has to have exposed props, right? And then a little while later we were saying, get rid of all of your exposed props, which may seem a little strange. But the story is that originally, all Chrome objects were 100% accessible to unprivileged code. So if the unprivileged code happened to get a reference to one single Chrome object, and there were lots of ways that that could happen, it was an instant arbitrary code execution, because you could just walk your way up to the global and call eval. And this is absolutely crazy. Like, this is one of the most bizarre things to me that we actually managed to survive as long as we did while doing that. So at some point, we invented these things called cows, where you had to explicitly whitelist the properties that were accessible, and we turned it on by default. And some people even made a Mozilla meme about me as like being, well, that escalated quickly. But I think it was the right decision to this day. So we then said, all right, you now have to whitelist the properties that are accessible from content. But this became to be a little bit of a problem as well, because people were using this as a tool to implement JS-implemented APIs, right? Because if you want to expose an object, you make the object in Chrome, and then you expose it to content. And these things were supposed to be DOM APIs. They were supposed to be DOM objects. And so we wanted to make them easy to use. And for example, if you return an array, we didn't want you to have to add .forEach and .map and all of the funny little normal properties that you would find on an array to your exposed props list, right? So then we started this game of ping pong where we would try to make them more easy to use, and then we would have a security bug, and then we would change it, and then they would be less easy to use. And I credit Luke somewhere in the back for finally pulling the plug on this and saying, like, this is totally ridiculous. Like, why are we doing that? Why do we have these objects that we are both super privileged and at the same time trying to make them seem like content objects? Like, why don't we just have two separate objects? And that is the solution that we eventually settled on, right? So the tools that you have in place of cows, I'm going to get to in a minute. But the key point here is that we have removed cows piece by piece, ripped them out. I thank a lot of you for helping to convert your APIs to JS-implemented WebIDL, getting rid of them. If you grep the tree, you will find some usages of exposed props left. This is because I kind of reduced cows to a very, very harmless subset of a few things that you can still do with them, which covered about 15 APIs that I didn't have time to go through. But the security problems that we saw with them are basically no longer there. We no longer do the funny prototyping remapping stuff. We no longer allow you to pull off callables. The situation is a whole lot better. So that being said, expose props is still totally banned, right? Johnny has a script running on every check-in, and if anybody adds a new expose props, I will hunt you down and back that out immediately. So don't do it. You shouldn't have a reason to do it. And if you ever feel like you do have a reason to do it, please come talk to me, and I will show you the right technology to use. So what is that right technology? If you're doing DOM stuff, you almost certainly want to use JS-implemented WebIDL. This is the binding machinery that Andrew McCrate wrote about a year and a half ago, and it's really awesome because you can basically implement your JS in an XPCOM JS component, and you can write a WebIDL file. And then at compile time, we will generate a very solid set of C++ binding code such that we can actually expose bona fide objects to content. These are regular objects, just like document and XML HTTP request that you find in content. And when you operate on those things, just like any other DOM object, it will have all of the proper semantics that Anna and Hixie come up with. And it will tunnel down into C++ code, down to where all the DOM stuff lives. And if it notices that it happens to be implemented in JS, it will tunnel it back up. So these bindings have come a long way. There's a lot of documentation about them on MDN, and most of the people who've worked on them and implemented them are here. So if you ever have any questions, feel free to come find us. But JS-implemented WebIDL does not necessarily work if you are not doing things that are baked into the browser, things that don't compile with the browser. So a great example of this is add-ons, right? Add-ons sometimes want to expose things to content, but they don't have the ability. Jesse, was that just a +1 for add-ons? Yeah, +1 for add-ons. And they sometimes need to expose things to content too. And so this is where we introduced a separate toolbox that you could use in JavaScript to safely expose objects to content. The most basic one isn't really a separate toolbox at all. It's simply the extension, the logical extension of all of the work that we've done on X-ray wrappers, right? Because if you never wave X-rays, you can still safely create objects in content by just invoking constructors, right? If content win is an unprivileged page in your privileged code, you do new content win.date, that will safely, over X-rays, invoke the date constructor, create a date object in content, and then hand you back a reference to that date, which itself operates over X-rays. So you can create objects, you can create dates, you can create typed arrays, all sorts of good stuff. If you want to expose functions and code, we have this thing called export function, right? CU is components.utils. And the basic idea there is that it's more or less like just giving a reference to your function to the content, except you have a security barrier and the function appears a whole lot more normal than it would otherwise, right? So effectively what we do is we just create a function, a regular content function, that when you invoke it will tunnel back down to C++. This is kind of like the obvious pattern here of how it always works. Tunnels back down into C++ and then goes back up and invokes the Chrome function. This is cool in two ways. First of all, the function looks normal from JavaScript, right? It has a normal prototype chain, does all the normal stuff that a function would do. And it means that we can apply all sorts of clever security heuristics of the stuff that's going through. In particular, we can filter out stuff that content should not be able to pass to Chrome, like a cross-origin location object. The final piece is components.utils.clone_into, which effectively gives you access to the HTML5 structured clone machinery. So if you have some large object that you want to create in content, right? Like let's say you have some tricky manifest of some object and you're defining this whole thing in curly braces and it takes half a page. If you want to create that in content, you can simply create it in Chrome and then invoke components.utils.clone_into, and that will create the exact same object, but a copy of that object separately in the content scope. And there are a couple little funny things you can pass to this, right? You can pass wrap reflectors such that it will do cross-compartment references to anything that's not clonable, like a DOM object. The details of all this stuff are on MDN, and I'm also happy to answer questions about it, but I'm not going to go into too much detail now. So these things are very useful for Chrome, Chrome privileged code to expose things to unprivileged code. But it's not just for Chrome. And we have these things called expanded principles. And I know a lot of people have wondered about what these are, so I thought I would take a brief moment to explain them. Gabor back there invented them against the will at the beginning of me and Blake. We both thought it was a bad idea, and then he insisted, and then it turns out it was a really great idea. So I'd like to thank him for that. The basic idea is that we have, in these asymmetric privilege relationships in JavaScript, we have this idea of subsumes, right? Subsumes is the fundamental question that we ask about security. Does this global subsume this global? Does this principal subsume the other principal? And subsumes basically means has access to, has full view of, right? Has strictly more security privileges than the other thing. So obviously, if two things are same origin with each other, they subsume each other. If they're not, and they're regular content pages, neither subsumes the other. Everything subsumes itself, and the system principal subsumes everything. But there were situations, specifically with Jetpack content scripts, where we wanted to create something that was able to view one or more pages from content domains safely, right? Like if you inject a page mod. But we also didn't want to give those things full system privileges. And so that's what came into the idea of expanded principal, where you can create a principal, create an origin that is a collection of a bunch of origins that subsumes all of those origins individually while not having those origins subsume it, but does not itself have the ability to run arbitrary code on your computer. So this is, the kind of principal lattice that we have, right? Everything, by the way, also has an implicit self-edge, so I didn't want to put that on the diagram itself. But at the top, we have the system principal, which subsumes everything. At the bottom, we have normal page principals from different domains. If they're same origin, they subsume each other. If they're not same origin, then they don't. Over here, we have null principals. Null principals are basically these nonce or unique principals that you see in the HTML5 spec. That's what you get when you have a sandboxed iframe or in certain situations with a blob URI. And up there, you have an expanded principal, which is basically an array of other principals, right? So that subsumes A.com and B.com, and the system principal subsumes it, and yeah. Jason? Okay. So principals, Gish.
So A does not subsume sub.a.com or vice versa, even though sub.a.com said the document is domain to A.com and then.
Right. So subsumes as a relationship. Sorry. The question was about document.domain and the fact that sub.a.com can become same origin with A.com, right? Document.domain is one of these funny things. It was this last little thing I was going to maybe mention or maybe not. Principals and origins are mostly immutable, but they can change ever so slightly with this absolutely terrible feature that was implemented back in the day and that we are working our darndest to get rid of. But a lot of the web, like eBay, depends on it. And that's where you can set your origin essentially to be anything of your subdomain. To be, if you're sub.a.com, you can then become A.com, but only really same origin with other things that have also set their document.domain to be A.com. So the basic answer is that no, we absolutely don't consider that when we're doing our basic security computations, right? Because sub.a.com is cross-origin from A.com. And if you do change your origin via document.domain, then we recompute all of the security relationships. We actually recompute all of the security wrappers because stuff may have changed. But in general, we do not consider document.domain. So this is the big one. I think a lot of people have been wanting to see something like this for a very long time, and I'm going to go through it. Because this is something that when you hack on XP Connect and somebody says, like, okay, well, I have this thing touching this thing, what kind of wrapper do I get? And I say, oh, yeah, you get that wrapper. And that's sort of like the Oracle role, and it's because I have a mental model of this flowchart in my head. And I've never bothered to tell anybody else about the flowchart because it was always changing all the time, and it would just be really confusing. But I'm going to post this online. It's not likely to change very much from here on going out. So the first thing, I'm going to go through it. We are computing a wrapper from global A into global B, right? Global A wants to touch something inside global B. So we examine the security relationship between A and B. Does A subsume B, and does B subsume A? So in the first case, we have A subsumes B, but B does not subsume A. That is the situation of Chrome code, privileged code, touching unprivileged code, right? Because the Chrome code obviously subsumes everything, and the unprivileged content code certainly does not subsume the Chrome code. And that is this asymmetric privilege relationship which is at the core of our architecture and the core of Slaughterhouse. So the next question we have is, did you wave X-rays? If you did not wave X-rays, then you get the normal default safe by default behavior. Then we come to this question of, are X-rays supported? Right? Do we have meaningful X-rays to give you for that object? If yes, then you get a normal X-ray wrapper that you can safely use with all of the engineering effort we've put into it, and that gives you proper access to the things you want while keeping you secure. If we can't X-ray, then we give you an opaque wrapper. Rather than giving you something that's unsafe by default, you get something that's safe by default. It will say it's opaque, and you have the ability to wave it. But probably you shouldn't. So that's where we are here. Then we rewind back here. Blake, you're going to love this. Then we have the case where A subsumes B and B subsumes A. This is the normal case of things being same origin on the web. They basically have the same principle. In that case, you go straight across. You get a transparent, vanilla, normal cross-compartment wrapper, and you can't even tell it's there. It just forwards everything across. The last case is that A does not subsume B, right? The thing that is trying to access the other side does not really have the access rights to see it. And in that case, it doesn't really matter what relationship B has with A, right? The point is that this shouldn't really be happening to any significant degree. We don't want to really let much through. So then we just come to this question, is it an object which the HTML spec specifies must be partially available cross-origin? And those two things now are thankfully just window and location. So if it's window location, then you get a filtered X-ray wrapper, which we call a cross-origin X-ray wrapper, which lets just a couple of things through. And if not, you get opaque, because you have no business doing that. So the cool thing about this is that, I can tell you all the ways in which you might normally encounter these things in Chrome code or in regular web code. But we get these relationships no matter what, right? So even if some silly extension grabs an object and sticks it somewhere where it totally doesn't belong, which in Chrome is a security bug, for us, we just follow this flowchart, compute the appropriate wrapper, and it's absolutely fine and safe. There are some special cases. Johnny? There are some special cases. Things that I don't bother putting on this because you shouldn't really need to worry about them, right? There are the case of vestigial cows, those little things that we have left. There's the question of when it's opaque, is it callable or non-callable if it happens to be a function. There's this thing called want X-rays, which is basically a deprecated feature we did for Jetpack, so don't worry about it. And there's the case of enable privilege, which will crash if you use it outside of our automation harness. All of these are special little cases, but we don't have to clutter up the actual security code with them. They're just, one little thing at the top of wrapper factory : rewrap. That is the source of truth for this. Did that answer your question, Johnny?
Yeah. Also, expanded principles. Exactly right.
Oh, the great thing is that expanded principles fit into this. Because as long as expanded principles have a definition of subsumes, which they do, right? That's what they do. An expanded principle subsumes all of the things in its array. None of the things subsume the expanded principle back. And the system principle subsumes the expanded principle. Also, expanded principles subsume each other if they have all of the array elements that the other one has. Then, as long as you can define what subsume means for an expanded principle, you can just follow this flowchart. So that's why subsumes is really the basic building block of security decisions in our code. So this is something that people ask a lot about, is what different types of globals do I have, right? People have code that's running somewhere, and it's like, oh, I don't know, is this a window? Is this a what? So the obvious DOM global that we have is window, right? When you're running any DOM code, stuff that runs on the web, your global is basically always window, or it's worker if you happen to be running on a worker thread. For internal stuff, we use this thing called sandbox a lot. Sandbox is basically a kind of catch-all, throwaway global that is, that doesn't need all of the funny window stuff. You just need a global with which to execute JavaScript. It's kind of analogous to the new ES6 new global stuff, but it's separate. And we use sandboxes for things all over the code base whenever we just need a global to execute things in. Like for little throwaway scopes, like, oh, we don't necessarily trust this code, let's execute it in a sandbox. We use it for XBL scopes. We use it for add-on scopes. We have these things called junk scopes. By the way, if anybody ever wants to use the junk scope, you have to ask me first. That's the rule. There's a comment about it. Don't do it. Then we have components and JSMs. This is oddly known as the backstage pass global. I think the idea is because it's like, it's kind of in the back and it's also very privileged. But when you load anything in a JavaScript implemented component, like XPCOM, it's got a contract ID, all that kind of stuff, or if you have something in a JSM, that's the global you have, and it always has system PC boundary when you're running electrolysis. And also, I believe, you get the same stuff on D2G.
I think there are also service worker globals now.
God help us. So we have other types of protections, too, that came with Slaughterhouse that sort of didn't fit anywhere else. So I'm going to talk about them very briefly. But the membrane concept is very powerful. And one of the things that we really want to do is to prevent content from sticking objects that don't belong on the Chrome side of the boundary. Because Chrome can see everything, right? And so if content wants to, for example, view a cross-origin location object, which it's not supposed to do, a really handy trick is to somehow pass it over to Chrome, which can see everything, and then convince Chrome to stringify it, right? And stringifying isn't the hardest thing to do in JavaScript. You just have to concatenate it with, quotes or new string it or something, right? And because Chrome is allowed to see everything, Chrome gets the full location object in all of its glory and converts it into a string, and then it's sometimes easy to pass it back. So the great thing is that we have boundaries on all of the methods, all of the mechanisms by which content can pass objects to Chrome. We have it on export function. We have it on JS implemented WebIDL. We have it on the vestigial Chrome object wrappers. And we can do these checks on all these things to make sure that content is not passing anything that doesn't belong. If you really want to opt out of this, when you're doing export function, you can pass this little option called allow cross-origin arguments true. Be very careful about that. That is potentially something very stupid, but maybe you can use it if you're careful. So there's always more stuff to do. There's a couple different things we want to do on the script security architecture, but most of it probably isn't all that interesting to people here. We want to make it so that the subject principal is only something that you can access in C++ when there's actually script running. We also want to dial down and remove the situations where we accidentally run script without intending to. And that's sort of part of what this AutoJS API, auto entry script work is about. I'm happy to talk about that more, but I'm not going to bore everybody with it. The last piece that I really wanted to talk about that I think people are going to, really should know about is the stuff we did for electrolysis, right? Because I found myself thinking that, okay, Slaughterhouse is basically 50% of the important security work, that's of what I viewed as the most important, exploit reduction security work happening in the browser. And E10S is obviously the other half. But really, much of what E10S was about and what made E10S possible is our wrapper and proxy technology. Because E10S as a project was basically abandoned a bunch of years ago because it was going to just break compatibility with too many things. And so we came back and we said, we will solve that problem with wrappers. Really, really complicated wrappers. So the two things we do there is we have what are called cross-process object wrappers, or CPOWs, which means that we can actually give references to objects that aren't, like if you've got some add-on that wants to touch an object that's not even in its process, we can give it a reference to it, right? It's just this funny wrapper that then goes and does all this IPC stuff and calls across the boundary and calls back. That stuff is super complicated and super awesome, and it's kind of a miracle that we're able to do that, but it works. And then we also have the case where we have all these add-ons that are running in privileged code in the parent process that are expecting the world to be in a way that it just isn't anymore. And so rather than breaking those add-ons, what we do is we hoist all of the add-on code now into its own compartment, and then we give it its own little world of security wrappers, right? These are called interpositions, or we implement them with this thing called add-on wrapper. And the basic idea is that we can say, okay, well, this thing we can tell is the tree-style tabs add-on. So we're going to apply funny behavior that it expects for preferences and for event listeners, right? And we can write these things in JavaScript so that every time we encounter a broken add-on, we can literally just embed special handling for that add-on into the browser. And it doesn't cost us anything, right? We just write it in JavaScript, and it only gets applied in situations where we know that buggy add-on is running in its own little lockdown compartment. So this lets us have our own progress and our own invariance and doing things right in all of our code, and we can still support all of the buggy stuff in a compatibility mode. So, I think that's pretty cool too. So yeah, it's now like 3:15. We technically have like 45 more minutes. I'm guessing a lot of people are sick of this, but I'm happy to answer more questions if people have them. Throw up your hand. Okay. D. Hilbert.
Per add-on, we have to know what we need to do.
Right. So the question was, with interpositions, does it require a specific whitelist per add-on? And the answer is yes. We notice a broken add-on, and it's on areweetensyet.com, and this is something that's broken. And we talk to the authors, and they're not going to fix it. And so what we do is we go and add something into our interposition code, and we register it as something that only gets applied for things with that add-on ID. Which means that then if we find some other buggy add-on that has the same problem, we can just trivially apply it there as well. But add-ons don't get it by default, which means that we don't have to propagate the buggy behavior forever.
There are some things that are for all add-ons unless up to down.
Oh, right. And it was pointed out that there are also some shims, actually, that are for all add-ons because so many things depend on it, and that you would explicitly opt out of if you want to have the correct behavior. I think?
Sorry, I may have dozed off during this part, but the union principle, or expanded principles, I guess you call them, I missed exactly what problems are those solving?
Yeah, so the question was, Steve may have dozed off, and what problem do expanded principles solve? And the answer is that there are some situations where we want to give scripts, for example, Jetpack content scripts, Grease Monkey scripts, etc. We want to give them access to content, potentially one domain versus of content, or potentially several. And we want to put them in an asymmetric privilege relationship with the content, right? Like, we want them to have X-ray wrappers, and we want them to be able to see the content, but the content shouldn't see it back. But we also don't just want to give it system principal, because when you give things system principal, you're playing with really high stakes. And so that's basically the idea, right, is that you can give things the least privileges they actually need, such that in the most basic case, this thing has no extra privileges than the content it's operating with, except for the fact that it has like strictly more privileges than the content. So it affects their security relationship, but it doesn't give the content script any extra stuff. D. Hilbert.
So with like a Grease Monkey script that runs on gmail.com and mail.google.com and googlemail.com would be like an example of that then?
Well, right. So that is, I don't know exactly how the question was, is a Grease Monkey script that runs on gmail.com and mail.google.com an example of this? It could be. I don't know their precise architecture and whether they reuse content scripts or whether they just create a different one each time. That was the original use case for them in Gecko, which is why Gabor, who used to work on who does work on the DevTools team, implemented them in the first place. But even in the case where you only have one item in your whitelist, they're still useful because they grant you an asymmetric privilege relationship with the content you're working with.
So, what is the principle or the goal that content script or add-on?
Content scripts or add-ons?
Yeah, the goal that a frame script or content script.
Okay, I see. So the question was, what is the global that frame scripts and content scripts and add-ons run with? So I think the answer for those is different. For frame scripts in particular, which is something where the parent process gives a script for the child process to run, that runs in the content frame message manager. Is that right, Ollie? So that's basically a special system privileged Chrome global that runs in the child process. Add-ons run in one of several types, depending on what the add-on is. If the add-on is a Zool overlay, right, if it's just embedding itself inside of Zool windows, then it runs inside of a window, a Zool window. If the add-on is a JSM, if this add-on code is a JSM or it is JavaScript component code, then it's going to run with the backstage pass global. You didn't? No.
I have some questions. Do you want to talk a little bit about, given that all like new APIs are relying on, a lot of them are relying on service workers, and we still kind of put that stuff in workers in JS. What are we going to do?
So the question was, given that a lot of new APIs are using, being implemented on top of service workers, and that we can't yet implement JS implemented web APIs on workers, what's the deal? So that's a very good point. It doesn't even necessarily just apply to service workers. It applies to workers in general. One of the biggest pain points that we have is that sometimes when you go and you implement a nice API in JavaScript with WebIDL, we then come back and say, oh, sorry, you got to rewrite it in C++. And the reasons for that are kind of twofold. One of them is that the memory requirements of workers are generally much higher than things running in C++, that we've dialed that down significantly. And the other problem is that we do not have X-ray wrappers or any security wrappers at all on workers, because in general, workers are only running things from a single origin. So if we were to do this, then we would have to have these API components, effectively what we use now on the main thread, also running on workers. We would have to be duplicating them between all of the workers, which increases the memory requirements, and we would have to port our security wrappers over. None of those things are particularly out of the question. Up until now, there has not been a compelling, it has not pushed us enough to do it. But I think, Johnny, we were maybe going to have a talk about that this week, or maybe not. There was some talk about revisiting that discussion, or at least, I don't know. There's no talk about it. Kyle says there's no talk about it. It's not happening. Never.
Might have already covered this, but I have a situation where you have a website and they're inserting an advertisement or whatever, third-party script, which is not going into an iframe, it's going directly in. So the effective script origin of that is, let's say, foo.com and bar.com. They're sharing, basically the JavaScript scope, but I don't want the foo.com script accessing or invoking a method in, let's say, in bar.com. Is that possible?
So the question was, if you're loading a script from a third-party domain into your domain, like you do script source equals some cross-origin cdn.com/foo.js, and you want to run that script, but you don't want it to invoke any methods in your page, is that possible? It sort of depends. On the web today, probably the best you're going to get is iframe sandbox by giving it sort of its own domain. And because when you do iframe sandbox, as long as you don't do allow cross origin equals true, then it gets its own domain, so it's actually going to be cross origin with you. And so you can run script in it and then effectively pull the result out if it's behaving well. But there's also there's a research project that we've been sort of supporting from the Stanford guys called Cowl of sort of like information flow control stuff. That's kind of skunkworks, so it's not really usable at the moment. But using standard web technology, if you're going to run it in your own global, I think the answer is that you cannot prevent it from doing anything, doing any stuff like that. So if you want to sandbox it, you have to use iframe sandbox.